Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
My name is Jason Dworkin from NASA Goddard Space Flight Center. I study organic compounds from extraterrestrial samples like meteorites and asteroid Bennu.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest is Jason Dworkin. He is a senior scientist in astrobiology. He's also a project scientist. He's working on what's called OSIRIS-REx at NASA. So we're going to get into what the the scientific objectives of that mission is about, and we'll talk about his work with NASA. So welcome, Jason.
Thank you for having me.
Yeah, if you would, it's always good to start out with a little bit of background. Tell me, how you got yourself to NASA, and what we'll talk about your current project.
Well, that's a long story. I've been interested in the origin of life for a very, very long time. I like how things start. And my whole career has been a gradual restricting of the variables on the origin of life chemistry, starting in high school where I was doing an internship at the University of Houston, studying origin of life chemical reactions to the same thing in graduate school. Then I got a postdoctoral fellowship at NASA Ames, where I was studying the precursors of life based on telescopic observations of making laboratory stimulants of the extraterrestrial ices. Then I was hired at NASA Goddard in 2002, where I started a laboratory studying meteorites and their organic chemistry. So then further understanding, instead of having observations that were limited by the imagination and by what little we knew of the ancient Earth and ancient terrestrial chemistry, to we knew a little bit more about telescopic observations, but not to the level of detail that I needed for my organic chemistry to look at life molecules, to then studying meteorites, which are fragments of the early solar system that actually contain the chemistry that were happening around the origin of life, to now working on the OSIRIS-REx mission, which collects the material from asteroid Bennu, a small primitive asteroid, which is a leftover of the formation of the solar system, and then studying that in the laboratory. So that is not only a piece of the ancient solar system, but one that we know where it came from and have a chain of evidence of how the sample was acquired and is being analyzed.
Okay, so what is the OSIRIS-REx project about? What does that stand for, first of all, and then what's it about?
The OSIRIS-REx is a NASA mission led by Professor Dante Loretta at the University of Arizona. He's the principal investigator. The OSIRIS-REx is an acronym of the mission objectives. O for origins, SI spectral interpretation, RI resource identification, S security, and REx is regolith explorer. So that is to understand the origins of the solar system, the origins of the planets, and hopefully the origin of life. SI is to look at the spectra of an asteroid close up with a spacecraft, compare it with the telescopic observations, and then compare that with the sample. RI is to learn how to operate around an asteroid and how to hunt for resources for future asteroid mining. Security is to understand the impact hazard of this asteroid and others in general. And then regolith explorers to look at the regolith in great detail by the spacecraft.
Okay, so what is your specific role in the mission? And again, what are some of the mission goals? What information does it hope to collect?
So the spacecraft went to asteroid Bennu, which is a small asteroid about half a kilometer across, sort of the size of a small mountain or the size of a large building in diameter. Rendezvoused with the asteroid, took lots of measurements, spectra, images, 3D models, and then we actually touched the surface of the asteroid and collected a sample and brought that sample back to Earth and delivered it this last September 24th, 2023. That sample is now being analyzed by the science team, and we released a catalog of what the sample contains, all 121.6 grams of material that was collected, so that future researchers can write proposals to look at the sample themselves with their own ideas and techniques. We're looking at the sample to understand how Bennu was made and what that tells us about the ancient solar system.
What is observed so far? Can you tell from the direction, the speed, the shape, the tumbling of the asteroid, if it does tumble? Like what can be told about it already without having delved into sampling it?
So during the in situ campaign, that was from 2018 to 2020, we observed that Bennu is rubble pile, a loose collection of rocks barely held together by gravity, roughly sort of a top shape, roughly spherical, but it bulges out at the equator, and that's just due to that's the gravitational low. So things fall downhill to the equator. The surface has almost no gravity because it's so small. It's on the order of 6 micro-Gs, which is almost as little gravity as felt on the International Space Station. So there are rocks that get ejected from the surface, go into orbit around Bennu, fall back down, or are lost. These are very small stones that get thrown off from just tiny little actions, like perhaps from cracking of the surface, either from thermal changes as it goes from day to night and dehydration of the minerals, to perhaps even impacts of other micrometeorites that drive off these ejections of particles. We discovered that it is a very rough, rocky environment, very, very dark. So the sort of the color of fresh asphalt, or a little bit darker than that. We found that it contains hydrated clays and carbon-rich materials, veins of carbonate, magnetite, and these have actually been confirmed in the sample that we've brought back. We've seen some of these same things. We learned how to fly a spacecraft autonomously around a tiny object and have it rendezvous with the surface, doing in the process, garnering ourselves 2 world records for the lowest orbit around the smallest object ever made, and did some phenomenally small maneuvers.
But you orbited Bennu?
We did.
How much gravity does it have? How would you do that?
It's a very low orbit, very, very slow orbit, and we had to orbit around the pole, from pole to equator, having the spacecraft always in sunlight. So one, we can make sure the spacecraft was always had power, but also because the gravity is so low that the force of solar pressure from the sun is on the same order of magnitude. So we had to balance the forces on the spacecraft from orbit.
Did you have to orbit? So let's say I'm looking at the Bennu and the sun is behind Bennu. Did you have to orbit in the same plane and the same distance from the sun, or I guess you wouldn't orbit sun side, non-sun side, non-sun side, because then you'd get a very disparate amount of force or solar pressure, right?
Exactly. So we always orbited at the day-night plane on. So if you were on Bennu looking up, it would be dusk or dawn when the spacecraft went overhead, if that helps.
Does Bennu tumble, or is it's fixed in place?
It rotates. It doesn't tumble. It has a very regular rotation of 4.3 hours per rotation, but it rotates retrograde. So its north is our south, although there's by convention.
Huh, weird. So if the satellite is orbiting this way, is the satellite turning? Because otherwise I would think the sun-facing side part of the satellite would would be heated and the backside would be cooled.
Oh, we want that.
Heat exhausting.
It's
okay?
We want to keep the cameras from getting too much sun on them. We want to keep the radiators cold. We want to keep the solar rays always in the sunlight. But one of the things that the spacecraft has is that the solar rays are articulated, so we can move them. So we can have the solar rays point at the sun no matter what angle the spacecraft is at. We could even tuck them up so the spacecraft is in a Y configuration. So when we went to touch the surface, collect the sample with this 3-meter long pogo stick that has a sample collector on the bottom, we could make sure that if the spacecraft tipped a little bit, it wouldn't clip the solar arrays. That was really important because Bennu was way, way rockier than we had thought based on our observations from the ground. We had lots of measurements from space observatories and from the Arecibo telescope, Goldstone telescopes that gave us a lot of confidence in the shape of the asteroid, but it confused us as to how smooth the surface was. We thought the surface would be very smooth like a sandy beach based on what's called thermal inertia. That is how fast the surface warms up and cools down during this day-night cycle. And so that, based on that model, told us, it's going to be a very smooth surface. Turns out that it's actually super rocky with boulders everywhere, things that could destroy the spacecraft. And that was because it looks like the boulders are not very well consolidated, so that they heat up and cool down like individual particles, even though they're giant rocks. They could be very soft and crumbly, but we wouldn't dare touch them because if it isn't, then we lose our spacecraft. So as a
touch one, because of the super low gravity, what material would just, let's say, float around and could destroy anything near it? I guess it would come off and just be flung all over the place.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Well, we actually did that when we touched the surface. So we had to redesign our maneuver to collect the sample. We initially planned on using laser ranging to see where the limb is of the edge of the asteroid, have the spacecraft navigate itself down to the surface and contact within a 50-meter diameter ellipse. There wasn't a 50-meter diameter area on the asteroid that was free of boulders. So we had to redesign it to be able to navigate itself based on landmarks, use it from the cameras, to bring itself to an 8-meter ellipse, so the size of a couple of parking spaces, as opposed to the size of an entire parking lot. And this was all done autonomously because this happened when the asteroid was 8.5 light minutes away from the Earth. One-way light time was 8.5 minutes, so you can't just steer it with a joystick. You send a command, you wait 18.5 minutes, the spacecraft gets the command, then does it, wait another 18.5 minutes, and then you know that it happened. It's not possible to drive that way. So it's all done autonomously.
How did the spacecraft orbit Bennu first of all, and then, so it's translating through space. I mean, also, where is it going relative to the sun? Is it coming in along the line of the planets in our solar system and going to go out that way, or is it coming perpendicular to the line of planets? Where is Bennu moving to?
Bennu's orbit is almost the same as the Earth's orbit, which is also why it's a potentially hazardous object. It has a slight inclination, about 6 degrees, and it goes just inside the Earth's orbit to just outside the Earth's orbit, of from up to about 1.2 AU. So it doesn't cross Mars's orbit, and doesn't cross Venus's orbit.
When did it get entrained in Earth's orbit, or in Earth-like orbit?
Well, we're working on figuring that out, but only a few million years, it looks like, or several million years.
Okay.
So we will be looking at samples to get more detail on how long it's been in near our space. We have some models that tell us based on the boulder population and the crater population, but we'll know really for sure as we're looking at solar particle tracks in the sample as we're starting to study it.
Is it going to move through any points in space, like Lagrange points, that would maybe slow down its motion or alter its trajectory a lot?
No, the biggest alteration comes from close approaches to the Earth. So the next close approach will be in the year 2135. And when that happens, if it lines up just wrong, then it could be set to collide with the Earth in sometime between 2175 and 2195. So it's a very low probability, and we we will be able to use the data that we collected while at Bennu and the samples we have in our collections now, so that in 2136, if Bennu goes past the Earth just wrong, future scientists, engineers, politicians, managers, and the public can make decisions on what to do about that, how to deflect it. For example, using what we learned from the DART mission last year on how to deflect asteroids.
Oh, what was learned from that mission?
So in the DART mission, there was asteroid Didymos has a small moon that's also a roboplanet. It looks a lot like Bennu, but much smaller. And they shot a spacecraft to hit it. They just whacked it with a spacecraft, and that changed the orbit of that tiny moon. So to demonstrate that we can actually move an asteroid and shift its orbit a little bit. And so something like that would be a way of shifting the orbit of Bennu if it became necessary in 2136 or beyond.
Okay, so Bennu is in this Earth-like orbit. Is there anything else in space that it could collide with, or anything else that would change its trajectory, or again just the Earth?
The Earth is the biggest object in this area, and there's always the possibility of something else, but space is vast, and the odds are very, very low. Now it does get hit by much smaller objects. So I mentioned that we saw the debris coming up and going into orbit and being released, coming back down. That might come from micrometeorite impacts. We saw on the surface of Bennu other rocks that appear to have come from asteroid Vesta or one of its daughter asteroids. So there's a different kind of rock that isn't native to Bennu we found. And we also, the spacecraft was hit by a small meteorite, just a speck of dust that caused a little crater. They were able to observe happen and during outbound cruise as it was leaving the Earth going towards Bennu. Had no effect, but we were able to see that occur. So space is a dynamic space, but also a very large space. So the best bet would be its known predicted encounters with Earth.
Well, what about any eclipses? Would it ever interact with the moon? Or again, what if it comes between the moon and the Earth? Could that happen?
It could. It's again, the Earth is the larger body, but in the simulations that has been run up to the year 2300, there are no lunar encounters. But unfortunately, these are the Earth orbit, the Moon's orbit, and even Bennu's orbit is very, very well predictable, so we can understand these things. Now, Bennu's orbit does change a little bit in a non-Keplerian manner because it shifts orbital just a little bit because of something called the Tarkovsky effect. And that's when you have a very dark asteroid like Bennu is. It absorbs sunlight, and then it also later on emits that light as heat. But because it's rotating, the angle of absorption versus the angle of heat emission is not aligned. And so there's a tiny, tiny little push from that radiation of heat that can slowly shift the orbit. We've been observing that on Bennu since it was first discovered and seeing the orbit change by a few kilometers over that time, since 1999. And so this is one of the reasons that we want to track these sorts of asteroids, understand how the Tarkovsky effect changes their orbits so we can make better predictions. And we now have as good numbers we're going to get until 2135 based on our data so far.
What about solar flares? Would that dramatically change its orbit at all?
No, I would not.
Oh, really? So if a big solar flare hit it, it wouldn't do anything to move it?
The actual force from a solar flare is fairly small. This is the size of a small mountain, a half-kilometer sphere almost. So that would certainly ionize the surface and create X-ray emission, which we actually were hoping to see when we were there. We had a student instrument, which was designed to look for X-ray emissions when stimulated by solar flares. But unfortunately, while we were at Bennu, the sun was during a quiet cycle, and we didn't have any lucky solar flares that would give us that data.
Okay.
But the students still learned a lot about how to design an instrument and collect the data.
Again, how did we get into orbit? How did a spacecraft get into orbit with Bennu? Like, did it lay in its path and then it hitched a ride gravity-wise? Like, how did that work?
There's almost no gravity, so we had to approach Bennu and then apply the brakes, fire the thrusters to slow down, and then slowly approach Bennu. And we didn't just go into orbit once. We went into orbit 10 times. We go into orbit, get out of orbit. It takes almost no energy to move around. So there's a YouTube video called The Weather on Bennu that shows just how this spacecraft zipped all over the place. That allowed us to look at the asteroid from all kinds of different angles, all different lighting. We could go anywhere we wanted around Bennu. Our smallest maneuver was 0.1 millimeters per second, which is just a minuscule maneuver. That was a phasing burn, so we could line ourselves up with our sample collection site. And the largest was a 431 meter per second burn. I believe that was the asteroid approach maneuver to slow us down.
How big is Bennu? Like, what's the diameter? What's the size of it? Spherical at all? Is it potato shaped?
It's a 0.5 kilometer across, and it's top shaped. So roughly, basically round, but it bulges at the equator.
It's a half what across? How big?
500 meters.
So if this was to enter into Earth's atmosphere and hit the Earth, what would be the consequence? How dangerous is it?
Well, we don't want that to happen. That's what we want to know how to reflect it. But it would be a local disaster. It would not be an Earth sterilizing event, but it'd be very, very bad.
Okay. So it wouldn't be catastrophic. It wouldn't destroy all life on Earth, but it would, a very significant portion of it would destroy? Like, how bad would it be?
It would be regionally very, very bad.
How fast is it moving?
About the same speed as the Earth. So the rotation rate is 4.3 hours per revolution. But the orbit that's really controlled by the distance. And the distance is about the same as the Earth, so the speed on the sun is about the same as the Earth.
Is it going in the same direction of orbit, or is it going in the opposite direction?
So it moves in the same direction as the Earth, but spins in the opposite direction.
So how would it, what would make it either catch up to Earth or lag, or, it's orbiting with the Earth in a way, right?
Orbiting with the Earth, but it crosses Earth's orbit. It's not perfectly inside or outside of the Earth.
So it's like wobbling in and out of Earth's orbit?
Right. So it's the Earth is an ellipse that's almost a circle, and Bennu is a bit more of an ellipse. And so it goes inside the Earth's orbit and then outside the Earth's orbit. So it's a little more elongated than the Earth's orbit, so it does cross. It crosses at 2 points.
Is it ahead of the Earth or behind the Earth, or does it go ahead and behind?
It lines up every 6 years.
But again, so the other part of the time, is it ahead of it or behind, or it alternates?
Now this is all about orbital dynamics, and so it depends on where it is in its orbit. So at the closest part to the sun, the innermost part is moving faster than the Earth, and the outermost part, when it's furthest from the sun, is moving slower than the Earth.
Okay, so it's ahead and behind. Is that how it goes?
Right. It's just, that's just how orbits work when they're ellipses.
Okay, I understand. So now that they've landed on Bennu and done sampling, do we have a device that's sitting on Bennu and riding with it? That's going to be there long term, or did it have to come off, or what happened?
No, we didn't litter in Bennu. We did make ourselves a little crater when we collected the sample, but we didn't leave anything behind there.
You left. You didn't know what stayed, or no machine stayed?
No, nothing stayed.
Oh, okay. How come? Was it just too expensive to do so, or unstable, or what? Why?
It wouldn't really add any value. So we have to be very, very disciplined when you want to run a mission. So I'm very proud that we're able to complete this mission on schedule and on budget. We've even launched under budget. We're able to use that excess money to do more science, which is fantastic. And so it would be cool to put down put a flag on Bennu or a beacon or whatever, but it's not necessary. It doesn't actually do more science. It's just something that's cool to do. We have to resist that temptation because that's what drives up budget. So it's most important to set our priorities very, very early, and that was competitively selected. So we had to compete with other mission proposals to get this selected, and then stay within what we promised to do and not go crazy with extra stuff. And that said, we did put on some chips of people's names, and some of them went back to Earth, and some of them are still in space on the spacecraft. But that's much less expensive than putting a payload on the surface of Bennu. Now, the spacecraft is still in space. The spacecraft dropped off the sample return capsule that has the sample, but the spacecraft is still orbiting the sun and was renamed OSIRIS-REx, and that is going to rendezvous with asteroid Apophis in 2029 to study that potentially hazardous asteroid.
Yeah, I just saw we came into a different order here, but so the sample itself, was that returned to Earth, or is it still, was it analyzed in situ on the craft, or how did it get back here?
No, we did no analysis on the craft. We just stowed it away and brought it to a world full of instruments on Earth. We needed to collect at least 60 grams. We managed to collect up and return 121.6 grams to Earth. That is now, the majority of it is on Earth at the NASA Johnson Space Center in Houston, Texas. And there's a sample catalog. You can go to curator.jsc.nasa.gov and look at what we brought back. And even write a proposal to look at some of it yourself, assuming that you have the qualifications and the experience to use the sample wisely. So the science team will get about a quarter of the sample, Our international partners from the Canadian Space Agency and JAX, the Japanese Space Agency, will also get material, leaving 70% of it for future generations to study. So people can start proposing now, but also some will be reserved so that future generations, people perhaps not even born, using techniques not yet invented, can ask questions that we haven't even thought of. And so your listeners or their children can look at the sample. But if they just want to gaze at the sample, there's some is on display at the Smithsonian Natural History Museum. There's some on display at the University of Arizona Museum, and there's some on display at Space Center Houston near Johnson Space Center.
Yeah. When will the samples be analyzed? So it sounds like they're in custody and they're being divided. When will they be analyzed, and what is each team looking for?
The first analysis of samples started days after return and have been continuing. Samples are being allocated to science team members. It's a slow, meticulous process to make sure that that the curators can do their job, which is really challenging. Working inside of these bunny suits, and the sample is inside of a nitrogen glove box. So very thick gloves and windows, and they can't even use their shoulders. Only their wrists and elbows can actually to manipulate the sample. Anyway, material has gone out to scientists. I've been able to study some of my laboratory. We're expecting the majority of it to come in the coming weeks to months, but the science campaign is underway, and we're seeing all kinds of interesting things. Magnesium phosphate, which was unexpected. We've certainly seen that it's incredibly carbon rich compared to other samples, up to 5% carbon, which is a lot for a rock from space. There's certainly hydrated minerals that we've seen. We've been able to confirm the things that were observed by the spacecraft at Bennu. We're seeing organic compounds, amino acids, nucleobases. We've just begun, but there's already a lot of richness in this asteroid that we'll be learning from for many, many years.
But what does it tell you about the provenance of it? What have you learned about it so far?
It's too early to give much of that. We've only looked at, the whole team has looked at less than 1% of the sample, and my lab has only looked at 0.02% of the material. So we can't make any big conclusions about the origin of life yet, but we certainly went to the right asteroid. It is the carbon-rich, ancient piece of rock we wanted. It looks to be very exciting. It looks unlike any other meteorite or the Arago sample brought back by the Japanese Hayabusa 2 mission. There's some similarities, but a lot of differences. So there's going to be a lot to learn. It looks like perhaps the sample is too fragile to make into the Earth as a meteorite, which explains why maybe it isn't in our collections. It's reminiscent of some types of meteorites, but not the same as any of them.
I know it is total speculation, but understanding that, what at this point, you really can't say anything, or what is it hinting to you? It may be totally wrong, but what do you think so far?
I like to follow the data and not speculate, but we are seeing basic building blocks of life. We're seeing a very primitive, unaltered, hydrated, ancient material. Our spectral interpretation was accurate, that we saw magnetite, we see carbonate. So that tells us that we really understand how to interpret data from our spacecraft, which is fantastic. But it's full of broken up bits of mineral all the way down. So at every size scale you look at, you see just fractal complexity, which is interesting and also makes it a challenge to understand. Lots of beautiful crystals as the minerals were formed in this ancient world. It came from a large asteroid that broke up, and we are learning more about that slowly.
You think it came from a large asteroid that a piece broke off? So I was going to ask you, based on its orbit and everything, where do you think it came from?
So the orbital dynamics tell us it came from a breakup in the main asteroid belt millions of years ago, from perhaps asteroid Polana or Eulalia. Those are what the dynamical models give us. But we won't know a lot more than that based on studying the sample, but it'll tell us more about their parent asteroids and perhaps how it relates to other so-called Class B or Class C asteroids. That's based on the spectral type. So that's the spectral interpretation aspect of the mission.
So if this has, various minerals and hydrates and high carbon content, wouldn't that mean that at least some of the asteroids in the asteroid belt are the same?
Absolutely. Most certainly, and we now have a better understanding of what this type of asteroid is made of. So these are B asteroids, where it came from a C sub B asteroid. So it's a little bit different, and it shows that it's also a bit different. It's a robopile, which means that it came from a larger asteroid kilometers across that broke up, and this just reaccreted into this lump. And we are learning more about how it came together, looking at pre-solar material inside of the sample. So material that's older than the sun, that was swept up as the solar nebula was forming, and then some of it got put into this asteroid parent body that broke up and turned into Bennu, that went to the inner solar system and was encountered by a spacecraft from NASA and then brought back to the Earth. So billions of years of history we're able to look at, but it's just beginning.
So at what point, what will be the next milestone in the analysis of the samples?
So further allocation, we are working on sending samples out to the organics analysis team, and then looking at what we call stones of interest. So these are our larger individual rocks that we brought back, which seem to be in 3 or 4 different categories based on shape and density. So there's the angular kind, there's the hummocky kind, so like cauliflower, very lumpy. And then there's a mottled kind that has patches of lighter color on it, which might just be the hummocky that has layers. We don't know yet. So looking at bits of each of these types to compare them against each other, we've so far only looked at what's called aggregate. That is the tiny little dust that's come off of these big stones. We've not yet looked at any individual stones for their chemistry or mineralogy, only their shape and density. So there's still a lot to come. We've only just begun.
That's excellent. Okay. Well, where can people go and keep tabs on the analysis and the mission and everything?
Okay, so the website now is science.nasa.gov/mission/OSIRIS-REx, and that's the main website. There's periodic updates at blogs.nasa.gov/OSIRIS-REx.
Excellent. Well, very good. Well, thank you for coming on the podcast yesterday. I really appreciate it.
Been a pleasure. Thanks for having me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.